So today I will introduce Manin conjecture about rational point of algebraic variety, and it will be only a brief introduction, and I will try to show you how one can use directly series to study some sample example of this conjecture. So I need several definitions. So first I will define what we call absolute values. So definition. Let key be a number field or any field. For this definition, let's be a field. An absolute value is a map from the field to R plus such that it's vanishing if and only if it's zero, and it satisfies the following property. And it satisfies also the triangle inequality. And we'll say that two absolute values are equivalent if there exists some positive lambda such that they satisfy this inequality. And we define this is a equivalence relation, and we define also the trivial absolute value is defined by the absolute value of x is equal 1 if x is different from 0 and 0 otherwise. So this is just, I recall, the definition of absolute values. And we said that an absolute value is said to be is Archimedean if or finite if it satisfies the following inequality. So for non-Archimedean, yeah, non-Archimedean. Otherwise, we said it's Archimedean. So an example: if K is equal to rational fields Q, then we define for any prime P these absolute values and 0 if x equals 0. This is an absolute values, and we have this is non-Archimedean absolute values, and we have also the Archimedean absolute values defined by the absolute values we know. This is Archimedean. Okay. So now I will define the notion of place, or definition. So let key be a field. So the set of place of key is the set of the equivalence class of non-trivial absolute values, and we denote this set by V variation K, and this set split on two parts. So this set splits on two parts. The set of finite place and the set of Archimedean place. So this is the set of finite place, and this is the set of Archimedean place. So by using this definition, we can now define try to determine this set for number fields, because today we are interested by number fields. So absolute values and place of number fields. Okay, so for given number fields, so we consider it's a ring of integers, and we consider the set of prime ideals of K. So we know that for any x in Q star, we have this decomposition, this ideal factor as a product of prime with some power here, and this function give a variation. P from key define a function from 2 z. This is the variation, and we define from this, and this variation satisfy the following inequality. So you can verify by hand that we have absolute values, and so before this I just will recall on definition. So for for this decomposition we have so we can define absolute values by this formula. So P minus F P Vp of x, Fx it's different from 0, and 0 Fx it's equal 0. What is this number? Fp is the residual degree. So if you decompose for a prime number p, ordinary prime number, these ideal factors have a factorization of this form, and we know that we have the residual degree, which is the degree of the extension p over p z over p z. That you have an absolute values, which finite values. This is finite absolute values, and you have also Archimedean absolute values. And for Archimedean absolute values, we need embedding of the for any embedding sigma of key n r. For any real embedding, we define the absolute values x sigma by sigma of x, and for any complex embedding sigma of k, we define these absolute values by as sigma of the module to power 2. This gives you a class of finite absolute values of the number fields, and this the class of Archimedean values in the number field, and up to equivalence we have all these absolute values. So the set of so we have the set of finite valuation of k. It's equal to, there are no other one, p, and the set of Archimedean place, it's the set of sigma real or complex embedding of k. This is, if you know, the proposition. So this is classical result in algebraic number theory. So one important result we need, it's the product formula. This for a number field. So if you take for any x in T star, if you take the product of xv, where v is in the set of place, the products on all the place, then the result is 1. this is classical, and for example, to prove this, it's not so difficult. You have just to compute the product for V Archimedean of xv, and this is equal to the product of all the embedding of K, and this is equal to the norm of X. And in the other hand, if you compute the product of of V for V non-Archimedean place, then you can write this as a product for ordinary P and the product of P dividing P of P minus Fp Vp of X by using the definition I gave before, and this is equal to the product on P of the product of P dividing P of P F P minus Vpx, and you can see this is equal to the product on P of the product of P dividing P of the norm of the ideal P minus Vpx, because this is the norm of this ideal. The norm of ideal is defined by the cardinality of Yoki over P, and this is a vector space over Z Pz of dimension Fp. So this give you this formula. So, and from this you see that this is equal to the norm of the product of Vp x minus 1, and this is the norm of x u k minus 1, and we know that this is equal to the norm of x minus 1. So now by using this formula and this formula, star 1 and star 2, imply that the result. So we get the product formula, and this is important in the definition of the norm. And okay, so now we are ready to define height of projective space. Projective space P and Q with Q number fields. So for any variation of place of Q, we have an absolute values. So, and by using these absolute values, this allow us to define some norm from key V n plus 1 to R plus by using this definition. equal to so we have several definitions, but I will use the more standard one maybe. So for finite plus, we take the supremum of yi from 0 to n. If v is finite, and we define other ways. We define the norm by sum from 0 to n v f key v over r 1 over key v over r if v is Archimedean. So and we assume that the following condition. The first one is that the norm is equal 0, equivalent to equal 0, and we, strictly speaking, it's not a norm, but it must verify this condition. So this for any y in kv n plus 1, we and for any lambda in kv, we have lambda v is equal lambda v v, and we assume also that the function to R is continuous. So now give a proposition for any y equal y0 yn in key n plus 1, and for any lambda in k, if you compute the product on all the places of the number field key of the norm of the vector lambda y0 lambda yn, then this is equal to the same product without lambda. This is important, and this is why the product formula it's important. The demonstration proof it's easy by using product formula. V. So this is equal to the product on V of lambda V norm of and this is equal to the norm on V lambda phi, the product on V here are the norm of, and by product formula this is equal 1. So you get the result. And by using this proposition, now we are ready to define the height on projective space. So, definition. So we choose let M of family be an adelic, an adelic matrix. So what I call adelic matrix, it's family of matrix satisfying the assumption just I drop. And we define our height H M associated to this family of matrix on P and Q by the following formula equal so for any projective point. Here I use homogeneous coordinate. So we define the height of this point as the product on all valuation of the norm of the point and this is well defined by using this proposition, because if you homogeneous coordinates are defined up to a multiplicative constant, and this proposition tell us that the result of the product is independent on the constant. So this is well defined by the proposition. So in projective space over number field, we have way to some size to measure the size of point, and it's given by this height. An example, if key is equal Q, then if you take a point in the projective space P and Q, so you can assume that by homogeneity we can assume that the xi are integer and coprime. By homogeneity, we can assume that. So if now we try to compute HM by using the adelic matrix of this number fields, so we have the product of P in prime, P prime, which correspond to finite place, and in this case we have only one Archimedean place, and it corresponds to this give you this formula, and it's easy to see that this equal. So for finite place, we define this as the maximum of xi p for I from 0 to n, and here this is the the value at the Archimedean place. And if you compute this part, this is the product of P prime and of maximum from 0 to n of xi to power minus vp xi. But the xi are integer, coprime integer. So this maximum is 1. So the result is if in the case of projective space over Q, only the Archimedean place is pertinent in some sense. We don't need the finite place. But this is not the case for other number fields. So, for example, in Pn Q, by using this notation, you can choose any definition for this. So, the usual one is the maximum of xi, and you have also you can choose this one. You can choose also the Euclidean one. And for some consideration, maybe sometimes it is also interesting to take some polynomial on x1, xn of degree d, 1 over degree of p, etc. So you have many choose, and for each choose you have a height, and for each height you can use each of these height to compute the number of rational points in some subvariety of P and Q. And one interesting problem is to understand the dependence of this counting problem on the choose of the height. This is no trivial problem. And the choose of the matrix at the infinite place. Here. Now we want to do the same thing for more general algebraic projective variety. So I need today some definition from algebraic geometry. So I don't know if everyone is familiar with projective variety, line bundle. I know, but maybe not all. So I will recall maybe some definition. What is projective variety? For example, it's so projective space. For example, for Pn key, the projective space, it's the quotient of Kn plus 1 minus 0 by this equivalent class, where we define this equivalent class by the following. If and only if there exists some non-vanishing lambda such that yi it's equal lambda xi for all I. So this defines the projective space, and projective variety in some sense are, roughly speaking, variety defined by subset of So in projective space, we denote the coordinate for a point M. We define the homogeneous coordinate, and the homogeneous coordinates are defined up to multiplicative constant. So projective variety are defined by as the set of points in some projective space, such that, for example, it's the FR0, where F1, Fr are some polynomials, homogeneous polynomials. Pen de K. So, roughly speaking, we can define them by as the set of vanishing of a finite number of homogeneous polynomials. And we need homogeneous polynomials because the values at a point it's not really defined. But if the polynomial is homogeneous, the vanishing of the polynomial on a point is defined. The meaning of the vanishing of polynomial on a point, because and for example, you have also affine variety and affine variety. So here we work, so it's something which is defined, roughly speaking, as the set of vanishing of some polynomials where F1, Fn are polynomials. This is the basic affine variety. So on this variety you can define function, and function, the set of regular function on V, it's in some sense we take the polynomial, but we consider that two polynomial are the same, define the same function. It's the difference, it's vanishing in the set V. So in some sense, it is the same as the set of polynomials divided by the ideal of V, where the ideal of V is the set of polynomials vanishing on V. This is the set of function, and we define also, for example, for a reducible V, we define the set of rational function as the fractional fields of this set of the regular function. So we have a general algebraic variety. In some sense, it's we take a number of affine variety with V and with the sheaf of regular function of V, and an algebraic variety with something who for any point of V of this X, you can found a neighborhood U near around P, such that U and the sheaf of regular function on U, it's isomorphic to V for where V affine variety. So it's a collection, in some sense, collection of affine variety, which you patch together. Okay, just to give you an idea about what we mean by algebraic variety, but for persons who are not familiar with this, we can just take this kind of set or projective set as I defined. It's enough. So now I will define what is the line bundle. So a line bundle, so let X be an algebraic variety. So a line bundle L is in some sense consists on a map P surjective map from L to X. So L is also an algebraic variety, surjective map, and such that X has an open cover UE with the following. Two properties. The first one, over each open UE, your line fiber look like UE times K. So, which means that for all E and E, there exists some morphism if I from P E minus U to UI times K, and here you have UI, and here you have the first projection, and this diagram commute. It's a commutative diagram. And the second point, so which means that over P minus over this open, it looks like just UE times K. And the second point is that now we know what's happened over each open of trivialization, but you need to patch the data together, and this is in convenient way, and this is given by the second point. So for E, U, G in I, you have a map which is regular on UE and cap UG. This is the set of regular function on this open and non-vanishing, such that the transition map which defined by Fg composed with Fi, and this is defined from Ui times K to Ui cap Ug times K, and this transition map, so it's given by, so to the point xt, it associates. Here we have no necessary x, which comes from this commutativity, and here the t change to g x times t. Okay. So the gi, the function gi, verify the co-cycle condition which means they verify for all E, G, K K, and all x in UE in the intersection. Of course, if the intersection is not empty, it verifies GEK x equal GEG x GGK x. This is the co-cycle condition. And this is just this is in some sense necessary in order to patch together this set. So in some sense, you can, to have an idea, you have here your basis space X, and what is a line bundle? This is a family of vector space parameterized by the points of X. Here you have P minus X, the fiber over on X, and Lx is a vector space of dimension 1. And the L you can, in some sense, it's the union of this line, this parametrized line, and this family depend in regular way on X in some sense. This is the idea of so the one important point is the following. So the co-cycle condition characterize the line bundle up to isomorphism. Which means that if you, for a given family of functions GEG satisfying this condition, there is only one line bundle defined by this GEG up to isomorphism. Okay, so we have the trivial line bundle, which is defined by as you can imagine, it's only x times k, and the map P, it's just the projection. This is the trivial line bundle, and now for a given line bundle, one can define, we define for any x in X, we define Lx as the fiber, this is the fiber at X, and this, as you can see, this is isomorphic to K, and it has a structure of K vector space of dimension 1, which is canonical. So now we can define the Picard group of variety. So we have just to define first the tensor product of line bundle. So let L and G be two line bundle over X. So we define the line bundle L tensor Xi in you have just in some you have here x, you have Lx in any point Lx, and you have also Gx. So you construct this by taking the fiber on G as the tensor product of the fiber of L on X and the fiber of G on X. This is a vector space of dimension 1, vector space of dimension 1, so it's defined. And if you want to use trivialization, then you have just, if L is characterized by the trivialization G is G up to an isomorphism, and if G is characterized by the trivialization H is G up to an isomorphism, then you can define up to an isomorphism this as the line fiber line bundle characterized by the trivialization G is G H is G. So you have a group right, so the Picard group the Picard group of X is the group of class of isomorphism of line bundle, and the law it's tensor product defined by for a class L, the tensor product of the class of isomorphism of L and the class of isomorphism of G, it's the class of isomorphism of LG. So this is the Picard group. So sometimes it's defined. You have also while you can use while divisor to construct Picard group. You can also use Cartier divisor as, for good variety. They give the same group, and this is not the only way to construct the Picard group. But for today, this is useful for us. So. Examples for in projective space, we have a family of line bundle. So we have the what we call O minus 1. It is the set defined by x, y in p n key times key n plus 1, such that y it's in the line x. So the element of the project space it's also line of 0 on key n plus 1, and we define this set, so it's related to blowing up, if you remember the talk of yesterday. And this is an algebraic variety because it's given by in Pn key times key n plus 1 by equation, by algebraic equation xi y g minus xg y e equals 0 for all eg. So it is an algebraic variety, and we have an open cover of Pnq. So we have defined for all e from 0 to n u e as the set of x in Pn p such that xi is different from 0. So ui e from 0 to n is an open cover of x equal pn key, and we can define for any e from 0 to n. We have a map here, fi from p minus 1 ue to ue times key, defined by here xy. To xy you associate xyi, and this is an isomorphism, because if you know x and if you know yi, by using this formula you determine all yg. So this is an isomorphism, and this is the reason for which this is a line. So O minus 1 is a line bundle. And by using tensor product, we define, so, and the transition function, you can verify that the transition function in this case are given by this gx, it's equal xi divided by xg for any eg. And now we can define for any m in z, we can define O pn key m as the tensor product of O pn key minus 1 tensor product minus m. And this is a line bundle, and the trivialization are given by this formula. So it's easy to compute. And the last thing, it's if you have a map between a variety, and if you have a line bundle here you have a map f, and here you have a line bundle. So you can construct a line bundle here, which is pullback of L, such way that all these things commute, and it's, in some roughly speaking, it's the line bundle over X, such that the fiber over a point X, it is the fiber of L over the point Fx. Okay. Okay, so now a definition. So we said that line bundle over an algebraic variety X is generated by its, or effective by its global section if for any x in X and all section of this line fiber, there exists for x, it exists a global section such that Sx is different from 0. So what is a section? So gamma xl, it's the set of section of this line number. It's just the set of function sigma from x to l such that p composed with sigma equal identity of x, which means that for any x in x, sigma x it's a point of the fiber Lx. So a section it's of x here, so it's send a point x to a point on of the fiber, and it is a regular function, some such. And you can define also the section over an open of x, and it gives you a shift. And we said that the bundle is generalized by its global section if for any x there exists a global section which is not vanishing in x, which means that you can the meaning of this is that sigma x is different from 0. This is a vector space of dimension 1, so this gives you a basis of this vector space. So which means that you have a family of bases of this family of vector space, and this family of bases is regular. It depends on x. On when x move, you have here y sigma y. You have another basis of the vector space, and the dependence on the parameter it's good, it's regular. What is the meaning of? Okay, so now we have an interesting theorem which said that so for x projective algebraic variety, the set of global section and L line bundle, so the set of global section is finite dimension is a K vector space of finite dimension. So this is an important result. And why I introduced all this thing? Because the idea is in the first part we construct height in projective space. Now if x is a projective variety, we need to construct some height which will give us way to measure the size of point here. So the idea is to construct some embedding of x in some projective space. To construct some embedding, and now we have a height here, we have an embedding here. So for m in x, I can construct some height which is defined by this embedding and also by this adelic matrix, and the height of the point m will be the height, the adelic height here of the image of m by phi. This is a point of the projective space, and you measure his height by the height of the projective space, and this gives you a way to measure the size of the point of the algebraic variety. And to construct an embedding, this is related to the line, the existence of good line fibers. And this is why I introduce line fibers, and we have the following proposition. Let X be a projective algebraic variety and LO line fiber, line bundle. We assume that L is generated by its global section so we choose by a set of set S0 Sn of global section. So we can define a map from X to the projective space in this way. So for any define a map from X to Pn key in this way. So to point you have X here, and you have an open cover. So and for where you are here, you have this situation. Times Q. So if you have a section, if you look to the section Sky, the restriction of the section Sky, so it's sent a point X to a point here, and this point it sent this point to a point here X Sky EX. So in some sense, we can characterize the section Sky by the family of the function Sky E from 0 to n, where each Sky U is defined from Ui to K, just a sample function. So a section, it's a family of regular function from defined from the each open Ui. So if you have a point X here, so you associate to this point the projective point as K0 of X, and so okay, Sky, so S0 I, S1 I of X, etc., until N I of X, if X is in the open Ui. And this is well defined, because if you now if X is in the intersection of two open, then the difference of this the difference between these factors, it's given by the transition function. So this is well defined. Because you have S chi u, it's related to S chi prime u by the transition function g k prime. So which means that you have the same point in the projective variety. And so this map, which I will call phi, phi is well defined, and it's a homomorphism, and we can verify that the line bundle L, it's the pullback by phi of OPN K 1, and the section SI are the pullback of XI. This is the way we use line bundle to construct map. And conversely, if you have a map, isomorphism, morphism of algebraic variety, then L, which is the pullback of OPN key 1 of this line bundle, is a line bundle of X generated by its global section which are SI, the pullback of the function xi. And now if from this line bundle you use this construction to construct a map, you will get the same map at the beginning. So this is the reason for why we are interested on line bundle. So now just another definition. Okay, so X, let X be a projective variety, and L a line bundle. So we said that L is very ample if there exists an embedding E from X to some projective space, such that L it's the pullback of OPN key of L. So, and we said that L is ample if there exists M such that the tensor product is very ample. So now height and so let X be a projective variety and L be a line bundle. So for simplicity, I assume here that L very ample. So we have an embedding phi L from X to some projective space, and we can construct if L is very ample, so we choose let S0 Sn basis be a basis of the set of global section of L, and as I mentioned before, this set is finite dimensional vector space, so we can find a basis of this vector space, and we can use this function to define the embedding. This is an embedding. So if L is very ample, so you have just to choose a basis of the set of global section and to use this set to construct your embedding. I explained the meaning of this. For example, if you have to choose a cover and to do things, and as I explained before. So this now, if you have an adelic metric, as we defined before, so we associate to L and M, or height we define, or height associate to L and M, which function from X to R plus, and to a point M we define the height of the point M as the adelic height, so the adelic metric. To the adelic metric we have an adelic height on P and K, as I explained before, and here we have just to, so we define this, and this is the definition of the height of the point M. And it depends on the choice of the line bundle and on the adelic metric. So I don't have time, but this is not the more general constriction. We don't need L to be very ample. For example, if P it's the class of L, it's in the anterior of the cone of effective divisor. In this case, we can find a Zariski open subset of X and construct an embedding of this Zariski open subset, and things work in the same manner.
What do you mean by cone?
But you have the affected, the cone generated by the effective divisor. But you have to be in the anterior the class. The cone is generated by the class of the effective divisor, and the class of the bundle may be in the anterior of this cone, not in the bondage. And if this condition is satisfied, then we can instead working with X. You have just to there exists a good Zariski open set, but as you know, Zariski open sets are big. And you can do the same constriction. Okay, so, and Manin conjecture said the following. So so let X be a projective variety and L or line fiber, line bundle, and choose M adelic matrix, and so we denote the LM. This is a line bundle with the choose of matrix. So matrix line bundle. So we have let Px the Picard group of X, and lambda F, which is included in pic X tensored by R, the cone of effective divisor of X. We assume that the class of this line bundle in the Picard group, it's in the anterior of the cone of effective divisor. In this case, there exists there exists an integer e such that and an open and Zariski open of X U of X such that we have an embedding of defined by not L but a tensor product of L E time from UK to Pn K, and so we define, as in the case of a very ample line bundle, we define a height associated to this line bundle and to this choose of matrix by for any point M in UK, we define the height L H L of M as the height. This is the height in PNQ defined as before, and here you have phi A of M. This is just in the case of a very ample line fiber, we take here X, but here you restrict ourselves to some open. But there is K open are big set. So what the conjecture said there exist for good x. That's, so for good mean projective variety, and in the first formulation, good the meaning of good was Fano variety. But now we know that it's not the conjecture is not true for all Fano variety. So there are no exact formulation of the set for variety for which it's true. It must maybe it must be true for you have to remove some parts of Fano variety in order to have the conjecture. So for good x, there exists an integer EL which depends only on the line bundle, and there exists BL and a constant C which depends on L and on the matrix, on choose the matrix positive, such that the NB, which is equal to the number of integer point of a rational point in this Zariski open, it's such that the height it's less than B. It's equivalent to B power E L log B to BL minus 1 as B tend to infinity. And for example, for Fano variety, the conjecture predicts that EL must be 1, BL must be equal to the rank of the Picard group of X. Here I put minus 1, so I don't need minus 1 here. And there are also a prediction of the constant CLM, but it will, I don't, you need more time to explain this construction, but if you are interested, please look to the paper of Per, Emmanuel Per, his paper in Duke Journal, and he gives the description of this constants. What? Ah, it's here. Thank you. Ah, it's here, the constant here. The conjecture, it was proved in some cases, for example, for toric variety by Batirev and Chinkel and Salberger, and there are some other work in Del Peso surface, etc. But it's still largely open. I have also some work in toric variety. I study for toric variety the dependence of this asymptotic on the choose of matrix. So there are a lot of work on toric variety and Del Peso surface, but it's still open for young people. This is a challenge. It's okay. So no. I don't have time to give examples. No.
Not for Fano varieties, but then you said that for Fano varieties you have that B is the rank.
No, the conjecture was formulated for Fano varieties, but now there exists counterexample of Batirev and Chinkel, one counterexample, and now one knows what is the good class. think that maybe if you remove some exceptional class from variety from Fano varieties, it's maybe it's true for all Fano varieties except some pathological class variety.
There is a empiric version also, which is actually proven, and where they pass to a model in some sense. I don't know if it's neural model or so. This might be the good. You start with the Fano variety, and then you take a model of this. And
there are some in different directions. For example, I give I formulate this conjecture in the case of number field, but you can also work on global fields. There formulation for global field and for toric variety, for example, for on function field. It was proved by David Borky. He wrote a long paper about the toric variety, or Manin conjecture of toric variety for function fields. And he has also some work of motivic cases. So if you are interested by this part, maybe you can read the book of David Borky and discuss with him. Maybe discuss with him. Yeah.
Maybe the field, the number field k is fixed.
Yeah.
You do not say anything how these constants may vary when you vary the number field.
No, I don't. It's not
really
easy.
for fixed.
Yeah, for fixed. But sometimes you need to increase the fields. But the dependence on the fields, it's not easy.
Yeah.
Yeah.